In this video, I want to talk about the notion of the dimension of a vector space. When we're working with the vector space Rn, we often refer to it as having dimension n, or maybe we call it n-dimensional space. And the way this is often written is that, for instance, for just the real numbers, the number line, the dimension is 1. So we'd write dim r as 1. For R4, the dimension's 4. This is 4-dimensional space. And for Rn, the dimension's n. My question is, what about other vector spaces? If we're dealing with a vector space that's not Rn, so either a subspace of Rn or maybe some other vector space, like maybe those polynomial spaces we've looked at, what does it mean for that to have a dimension? Or is that a thing we should even think about? And I want to motivate why this is a reasonable thing to look at. So if I look at this vector space, the vector space V is going to be the set of solutions to this homogeneous linear equation, x plus 2y minus z equals 0. This is a vector space because this equation's homogeneous. And let's look at this graph. This red plane in the picture is the vector space that we're talking about. And even though this thing is a subspace of R3, it lives in 3 dimensions, it really looks 2-dimensional. It looks like the xy plane. And so I want to be able to say that the dimension of V is 2. Because in my mind, this thing is 2-dimensional. Let's look at another example. So here we're not just looking at the one equation, x plus 2y minus z equals 0. We're adding a second equation, minus 3x plus 4y plus z equals 0. And we have a homogeneous linear system. So the set of solutions to this, which I'm calling W, is again a vector space. And let's look at the two graphs. These are the two linear systems and their graphs. And the intersection of these systems is the set of solutions to this homogeneous system. So let's get rid of the planes so we can just see the set of solutions. And again, we have this situation where even though we're in R3, this looks one-dimensional. This looks like a line to me. And so I want to be able to say something like the dimension of W is 1. And finally, as an example, I want to look at one of these polynomial spaces. So let's choose P2, the set of ax squared plus bx plus c, such that a, b, and c are in R. But really what this means is it's just polynomials whose degree is 2 or less. And we don't really need to be looking at this graph because I'm not going to graph anything here. In what sense does this look like some sort of vector space? Well, we talked about this, that it really feels like if I have a polynomial, for instance, x squared minus x plus 3, I should be able to associate this with the vector 1 minus 1, 3. That is, I can put the coefficients in a vector, and we formalize this, kind of what this all means, but just thinking conceptually, we're saying, look, any polynomial can be associated with a vector, and the reason I draw arrows with draw arrows with tips on either side, a two-way arrow, is that this association goes both ways, right? We can take any vector and represent it as a polynomial. It really feels like this looks like R3. And so I want to say something like the dimension of P2 is 3. So I've given 3 examples where I had vector spaces that weren't Rn, but in each case, it really felt like we should be able to assign it a dimension because it looks like a copy of Rn in some sense. Now, so far what I've done is what people would refer to as ad hoc. So ad hoc means when you're doing things on a case-by-case basis without a consistent approach. Right, so for my first 2 examples where I had solution sets to homogeneous systems, I was looking at a graph of them, which doesn't really work as we get to higher dimensions. It's hard to visualize. And here I took a totally different approach where I was really looking at how I could write this in vector form. I want to unify all that and understand how can we given a vector space, decide what its dimension is, so that if you decided and I decided, we'd both come up with the same thing for the same reason. So in order to do that, I want to go back into Desmos, and I want to look at R3. So right now what I've drawn here is R3 with its standard basis. So recall the standard basis of Rn, we're just referring to the basis consisting of the vectors with 1 in one of the coordinates and zeros in all the other coordinates. Right? In physics or engineering, we'd call these I hat, j hat, k hat. In math, we'd call them the standard basis vectors. And this is one basis for R3. But R3 has other bases. So for instance, another basis is, let me erase what I didn't want to show you quite yet. Another basis is this one. So we've got the vector 1, 0, 1, the vector 0, 1, 1, and the vector 1, 1, 0. These three vectors also form a basis. Kind of scroll around. You can maybe convince yourself that these are linearly independent and that you could always find a way to add them together to get any vector you wanted. And we saw when we were working with determining whether something was a basis of Rn that every basis of Rn has size n. And so every basis of R3 has 3 vectors in it. And the logic, remember the way in which we used this was that if we were trying to determine, for instance, whether this thing was a basis for R3, the first thing we checked was, does it have 3 things in it? Because if it doesn't, it's definitely not a basis. Now, to be clear, we have to be a little careful. It's not that any 3 vectors form a basis. So if I look at these 3 vectors, 1, 0, 0, 0, 1, 0, and 1, 1, 0, these are not a basis, right? These things are linearly dependent. I add the first 2, I get the third. They only span a 2-dimensional subspace of R3. So any basis of Rn has size n. This gives us a nice way to define dimension for other vector spaces. So I'll scroll back up here to where we asked this question in the first place. What about other vector spaces? So for any vector space, we'll say that the dimension if V is a vector space, then the dimension of V is the size of any basis of V. So let's go back to our examples and confirm that this works in the instances where I wanted to call something a certain dimension. So this example, the set of solutions to this equation, let's flip back to Desmos' picture of this. The set of solutions to this, which I wanted to say of dimension 2, here's a picture, and I want to draw in 2 vectors. Let's see if I choose the ones I wanted to. That's not what I wanted. That would also work. These 2 vectors here, they're both in green, form a basis for this space, right? They're linearly independent and they span it. So this thing does have a basis with 2 vectors in it. All right, so our next example, W, that was this visually depicted purple line. A basis for W, no, I'm clicking on the wrong stuff here. I didn't organize it. Is this orange vector, right? Anything on this line can be written as a scaled version of this vector, maybe negative to flip it. So this has dimension 1 and it has a basis of size 1. That's great. Let's go down to P2 again. So what's a basis for P2? I think the most natural basis to choose is 1, x, and x squared. And this has 3 things in it. Right? These are linearly independent, and we can write any degree 2 polynomial as a linear combination of these. So this has dimension 3. So this looks pretty good, right? All of our examples are new definition of basis, or sorry, of dimension that corresponds to basis, gives us the dimension that we intuitively wanted based on our understanding of what dimension should mean. But there's a final question here, which you may have thought of when I wrote this, or maybe not. The size of any basis, there's two questions that come up, and it's all about this being well defined. One of the questions is, do we always have a basis? That is, if I'm defining the dimension of a vector space to be the size of any basis of it, what if a vector space doesn't have a basis? And every vector space does have a basis. This is not at all obvious, but it's true. So every vector space has a basis. And this, to actually prove this, requires significant work, not something we're going to do in this class. Then there's a secondary question. Okay, well, I believe you. Every vector space has a basis, but do they always have the same size? Because if the dimension is the size of any basis, what if I find two different bases for the same space and they're different sizes? That can never happen. Any two bases of a vector space have the same size. And this is actually somewhat surprising, I think, just that vector spaces are defined by these super abstract axioms. And it turns out that, yeah, we have this concept of a basis, and any two of them will always have the same size. And just to give you an example of this, we go back to P2. I gave you one basis, but another basis, for instance, would be x squared minus x squared minus 1, and let's say 1. This would also be a basis for P2, and we could write down lots of different bases of size 3, but any basis we write down for P2 is going to have size 3. When a vector space does have a finite basis, we call it finite dimensional. And in this course, we're almost exclusively dealing with finite dimensional vector spaces. Occasionally, I'll look at examples that aren't finite dimensional because there are interesting things there and they're incredibly useful. It's something that if you take more linear algebra, you'll certainly see and is of a ton of use. But we mainly study finite dimensional vector spaces. That is, vector spaces that have a basis that consists of a finite set. So in that case, the dimension is some number. But just real quickly, what about vector spaces that don't have a finite dimensional basis? I'll just give you one example. Actually, I want to. So an infinite dimensional example would be the set of all polynomials over the real numbers. This is a vector space. You can add, you can multiply by scalars, you have 0, all the rules are satisfied, but a basis for this space is not finite. It's all non-negative powers of x. So we have a basis, but it's an infinite basis. And again, we're not going to do much with this in this course, but I just wanted to point this out, that dimension makes sense even in infinite dimensional examples. So if we say that something's infinite dimensional, we mean that any basis for it is infinite.